Let's look at this problem. Number 2, determine the internal normal force. So we want to find out the normal force, the shear force, the moment at this point, at point H of the frame. So this is the frame, and assume that the support at A and D, A is a pin, so A is a pin, AY, and assume it is like this, and D is a ruler. D is a ruler, which means that there is one reaction up. So how could we do it? No, I should do the cut at this point, at H. The best is to look from the right. I should look from this side. Much easier. Why you have to put this? You have to put this distributed load and the other half. No, let's take as less number of loads as possible. So I'll look from the right. I'll cut it and look from the right. So I'll cancel this. But before that, I need to find out why this is like that. Well, and that way, so it's AY and dy. So I'm going to find dy. Since I'm going to look from the right, I need the reaction dy. So I'm going to do moment, summation of moment at A, and I'm going to assume this is negative. This is going to give you summation of moment at A dy times 5 for the whole frame, dy times 5, and of course these two reactions are not going to be included in the moment. You have 12 times 4 12 kilonewton per meter times 4, that's 48 kilonewton, and 16 times 5, okay, 16 times 5, so this is, it's at the center, 16 times 5, I'm going to leave it as multiplication is better, because this is 12 times 4. And of course, it is at the center. So dy times 5, this is positive. 12 times 4, this is negative, minus 12 times 4, and that is times the distance, 2 meters. And this one, this also will do a negative, 16 times 5, times the distance perpendicular, which is 2.5, and dy 16 times 5, okay, that's it, equal to 0. So now we could find dy from your calculator. Dy would be positive 59.2 kilonewton. I think in the example in the class he gave you this. Okay, so we did find the reaction, 59.2 kilonewton. Okay, up. And now let's do summation of forces. Oh, no, we don't need to find summation of forces at Y. We don't need. We need to draw the frame from H okay, so this is dy. It's going up. You can see here from here to here is 4 meters, and you have a distributed load from here to the point where you're gonna get a section. This is 16 kilonewton per meter, and you have 2.5 meter where you have the cut. Let me draw another color. So this 16 times 2.5. So this one, 16, sorry that I put the number very close to the equation, but it is 16 kilonewton per meter times 2.5. That is in the middle. That is in the middle, 2.5 divided by 2 here. This is 1.25. And the other one is 1.25. So what we need to find, we need to find out the following. The shear at this point, shear, we could call it shear H. And we need also the normal force. Let me do the normal force this way. Normal force H and the moment at this point H. And let's do the analysis. We are looking only from the right. You want to look from the left, you could, that's up to you. But I'm looking only from the right. So I'll do summation of forces at x. I will do first summation of forces at x equal to 0. We are looking only at this frame, half from the right. Let's look at what are the forces in the x. Nothing but an h. The normal force at the point h is 0. So there is no force normal. Let's do summation of forces at y. Summation of force at y. We have one force here, 59.2. And we have one force down. Look at this force, 16 times 2.5. That is a force down, negative. And we have the shear force. The shear force, I'm assuming it's up. So I'm assuming the shear force is up. There is no other forces in the y. So what is the value of VH? VH, okay, 59. The shear force would be negative. 16 times 2.5. Let me just do it. Let me see. 16. 40. Oh, that's going to be negative. VH would be negative. Okay. So negative 19.2 kilonewton. The meaning of this value, that is 19 kilonewton, and it is down. The shear is down from the right. Of course, the shear going to be up from the left. Okay, so it is negative VH. Let's find the moment. Summation of moment at H. Okay, so we have the moment of the H. It is, you could look at it, it's negative here. So it is minus. I'm assuming that this moment is clockwise. So negative moment at H. Of course, VH and MH are 0 because there is no distance that is perpendicular to that point that we should include that VH, and we should not include normal force and VH at this point. And then we have 16 times 2.5, and this is also negative, times the distance, 1.25. And now we have this force. This force will do a positive moment, counterclockwise. Times, of course, the distance is 2.5. 59.2 times 2.5, 16.25 times 16 times 2.5 times 1.25. Okay, minus MH. Now, well, this is going to be a negative moment. Okay. Let's look at this. This is going to be, hold on, this is going to be positive. This is going to be positive because this is going to produce a positive moment. It is, yeah, of course, this is negative. This is going to be producing a positive moment, okay? Okay, so this is going to be a positive moment. And this is going to be 59 times 2.5 minus 16 times 2. Oh, this is going to be a positive moment then. So the moment at H is 98 kilonewton and meter, and this is positive, which assume it is, oh, no. Our assumption was clockwise. So it is positive, so it is clockwise. Okay, good. So we are done from this. And I think this is a very easy question, but you have to be careful when you do the frame. Okay? So I'll do the third one in the next